Okay, so precision cosmology with cosmic voids. I would like to highlight that the work I'm going to present today is really the result of collaboration with many people all around the world. And I also have the privilege to work with many talented students highlighted here in bold: Joanne Verza, Christina Crash at Princeton, Rashi Panchal, and Sofia Contarini. So let's move to the outline of my talk. I will briefly introduce cosmology, the large-scale structure, and voids, and then move into explaining what are the observables that we can use to extract cosmological information from voids. I will focus on the void galaxy correlation function and talk about constraints that we have so far. Then I will present the void size function and talk a little bit about the void-void autocorrelation function. And finally, I will conclude with my take-home messages. So let's start with cosmology, the large-scale structure, and voids. We are nowadays in the era of precision cosmology. We have a standard model called lambda CDM that explains that our universe is in an accelerated expansion. And we know that this universe is composed of 27% of dark matter, 5% of ordinary matter, and 68% of dark energy. Now, because we don't really understand 95% of our universe, it's great to have good tools to analyze and study our universe. And one of the best tools we have is looking at the large-scale structure of the universe. So modern surveys allow us to access large volumes of the sky and make detailed maps of what we can observe and of the distribution of galaxies. And in this kind of maps, this nice pattern is known as the cosmic web, and we can see that we have groups very densely populated of galaxies, and then we have thread-like regions that are known as filaments, and then we have very empty regions, and emptier. We have very few galaxies in those regions. They are underdense galaxies, and those regions are called voids. Now, voids are particularly interesting for cosmology, and there are a number of reasons for this. First of all, because there is very little matter in voids, voids will be, by definition, dark energy-dominated objects. So because we don't understand dark energy, it makes perfect sense to look at these regions that were the first to be dominated by this component. The second point is that voids, with their low density and large-scale feature, mimic the current accelerated expansion status of the universe. Voids represent a sweet spot for potential deviations from general relativity, and those deviations will be, in effect, more prominent in voids. As I will briefly also mention today, voids are also generically sensitive to diffuse components, in particular, for example, neutrinos, given their underdense nature. Interestingly, voids allow us to go beyond what is traditionally done in galaxy clustering analysis. What we do in galaxy clustering usually is that we look at galaxy maps such as this one, and we take one random galaxy, and we will ask ourselves how likely it is to find another galaxy at a certain distance from the first one. And this allows us to construct the two-point correlation function. But actually, the cosmic web embeds much more information, and this information is what we can capture by using voids, for example, because voids are extended objects constituted by hundreds of galaxies. Voids also have multi-scale sensitivity because they have sizes that span from 10 to hundreds of megaparsecs. And we can hope that they are easier to model on the one side because we can exploit traditional techniques that we know really well, and on the other side because they are by themselves objects that are easier to model in the sense that their behavior is more linear. So for all these reasons, voids are great objects for cosmology, and it's actually the good moment to look at voids because we're going to have an impressive amount of data in the upcoming years. Here we have some of the surveys that are some ongoing and upcoming, and they will allow us to obtain lots of large-scale structure areas. So because voids need both volume and detail in observation to detect low-mass galaxies, we are really only now approaching the golden era for voids. And we also have very well-tested tools to detect voids in surveys. For example, the void finder that I use, that is called VID, is widely used, and it has been widely used for data analysis, a bunch of SDSS data releases. We have BOSS, eBOSS, but also photometric data, such as DES. It is also in use for the preparation of the next generation of surveys, Euclid, Roman, PFS, and DAISY, and has the advantage that it provides us with a detailed shape of voids. You can see here we have a slice through a simulation where we have galaxies, and the color of the dots gives us the mass of galaxies. And we can see the voids that are found by the void finder vide, which, by the way, is the French word for voids. And you can see that these voids will have very different shapes. So this really enhances the signal to noise for example, for application that need to measure the shape of voids in detail. So we have everything we need: large surveys, a void finder. What are the quantities that we wish to constrain? Well, of course, we want to constrain the content of the universe, the matter content, the content in dark energy. But we're also interested in quantities such as the growth rate of structure that tells us how structures and density perturbations grow with respect to the expansion rate of the universe. And sometimes we're going to refer to the growth rate of structure divided by bias, because, of course, we do not have access to the dark matter, but we have access to biased tracers of that film. And the last quantity that we're going to mention in this talk is the dark energy equation of states, that basically allows us to measure if dark energy evolves with time. So, our void finder is going to provide us with void centers, void radii, and tracers. How can we mix up those quantities to extract cosmological information? Well, we're going to combine those information to measure the void galaxy cross-correlation function, the void size function, and the void-void autocorrelation function. So let's start with the first one. The void galaxy cross-correlation function, the only void observable that so far provided powerful constraints. When we look at voids in data analysis, basically, those voids have very different shape. But in order to use them as a cosmological tool, we're going to stack those voids in order to have an object that, on average, in real space is spherically symmetric. Unfortunately, we do not have access to the real space shape. We have observed space, and the observed shape will be distorted along the line of sight, something kind of what we have right there, and this is because we observe angular coordinates and redshift along the line of sight. And the link between redshift space and real space, so the quantities that are going to provide us the link between these two spaces, are basically defined in terms of the cosmological model. So this means that really the link between the observed shape of our voids and the real space physical quantities is going to depend on some equations where you can see that we have the Hubble parameter defining our cosmological model and the angular diameter distance. Again, they will both depend on omega m and omega lambda. Now, it turns out that if we have those voids as standard spheres stacks in beams of redshift n size, we can stack them and apply the Alpha-Pisani test, where we basically say that because this object is a sphere, we know that its side, along and perpendicular to the line of sight, needs to be the same. So if we combine then this equation with the definitions that we have here, you can see that we get to this equation where we have the extent of the object along the line of sight that you get here, there, the angular size of the object, and here, those are all quantities that we can measure for a void. And here is a product that we want to constrain, dA times h of z, that embeds the cosmological dependence that we need. And then we can divide this value, this measured value, by what we expect it to be, so the fiducial value. So this is known to be as the Alpha-Pisani parameter. And it means that if I observe a survey, I will find my voids, I will stack those voids, and then I will measure their shape. If this ratio here is 1, it means I have used the correct cosmology to convert from redshift space coordinates into real space. If not, it means I need to correct my cosmological model. Good. So we have an Alpha-Pisani test methodology to test the content of the universe. But unfortunately, things are not so simple. We also have the presence of redshift space distortions here. In particular, galaxies composing by void will have peculiar velocities. And those peculiar velocities will induce deviations from the Hubble flow that will actually mess up with the Alpha-Pisani measurement that we have here. So it is easy to understand that if we want to exploit the void galaxy cross-correlation function, we need to take into account a modeling for the density profile, but also modeling for redshift space distortions. And this has been an area of intense activity in the past years. Let's start with the density profile. Is there a theoretical prediction for this density profile? Unfortunately, we don't have any that fits well what we see in observation. So what people have been doing is to rely on commonly used prescriptions, such as the fitting function that you can see here, that is able to fit voids of very different sizes and a different redshift. You see, this is a density profile of a void with an underdensity and then the wall enclosing our void. But then a second alternative is the use of a real space density reconstruction, which is something that I have developed a while ago during my thesis, and that we haven't used for a while until very recently. And basically, it involves reconstructing the density profile of voids from its projection. So by doing the projection, you lose the component that is distorted, and you are then able to reconstruct your void in real space. Now, because this real space density reconstruction does not make any assumption on cosmology, it has the advantage of being model independent. So we can directly apply it to data to extract the density profile of voids. The disadvantage is that it is very noisy because it relies on the Abel inverse transform here that is ill-conditioned. So of course, it was very hard to apply it until now when we have enough voids. Good, we know how to model the density profile. The second part that is a little bit more tricky is modeling the redshift space distortion pattern around voids. The very first papers in the field will try to just mitigate the effect of peculiar velocity, so removing the impact in order to perform the Alka-Pisani measurement. But actually, velocities embed a lot of cosmological information. And in fact, they depend on the growth rate of structure that will have a different value depending on whether, for example, general relativity is the correct theory. So we actually have now two mainstream prescriptions to deal and control redshift space distortion, and both have been applied to data. Let's start with the first one. The first one involves describing the velocities around void with a Gaussian probability distribution function. And if you do this and you assume a profile as a fitting function, the one I was describing before, you can model both the Alka-Pisani effect and the redshift space distortion in the framework of this Gaussian streaming model. And this was the very first application that we did, and we got some constraints on omega m at 11% precision level. And you can see that we got a measurement of the shape of void, this Alka-Pisani parameter, at roughly 1% precision. But then, a few years later, we tested a different model that is called the linear model. And it basically involves developing the void galaxy cross correlation function in a series of multiples. Now, it turns out that with the linear model, you can have a very nice equation that links quantities that you measure, the monopole of the galaxy correlation, void galaxy cross correlation function in redshift space, and the quadruple. And the only quantity that you do not know in this equation is the growth rate of structure. So this means that by measuring voids and then calculating the void galaxy cross correlation function, you can directly plot the monopole that you have here, basically the density profile, the quadruple, and then you can compare the two sides of that equation. And this allows you to get constraints on the growth rate of structure, where you can see that we have growth rate of structure as a function of redshift. And here you have the expected value in the framework of lambda CDM. And these are our data. So each one of these points is a void stack. And we have the low Z sample and the CMAS sample from the Sloan Digital Sky Survey. And this allowed us to get a 12% constraint on the growth rate of structure. Now, very recently, we decided to put together the best of all these techniques to try to obtain a state-of-the-art measurement of the Alka-Pisani and redshift space distortions about voids from the final combined BOSS sample. So basically, for this methodology, we account both for the Alka-Pisani and redshift space distortion. We use the linear model for multiple analysis that performs so well. And then we introduce the third ingredient, which is a model of the profile that we obtain directly from data, from the projection. In this way, this methodology is fully model independent. So here you have the sample that we have been using. We have number of voids and galaxies as a function of redshift, and here are the voids that we use for our analysis. We have roughly a little bit less than 6,000 voids, and those are all the voids that we get nowadays. And we can test our pipeline on MUX. So you can see that we have these points are from the max, and then the model is the line that you can see here. We have the monopole in blue, the quadrupole in red, and then a flat hexadecapole as predicted by linear theory. And then if you look at this model in 2D, you can see basically the contours of density that we get here. And we have in black the contours that we measure from the simulation, and the model on top of this is these white lines. And you can see it describes pretty well the underdense part in the center, and then the overdense wall enclosing or stacked voids. Okay, we can finally apply this to data. Of course, it is more noisy. But you see that we recover pretty well the different features of the void galaxy cross-correlation function. And again, we can measure the monopole, the quadrupole, and the hexadecapole of our void. And finally get constraints. So let's look a little bit at those constraints. Because of what I explained, you know that we will have alpha-Pisani constraint from the shape, and then we will also constrain the growth rate of structure F, because we're modeling the pattern of peculiar velocities around voids. And these are the constraints that we get on epsilon, the alpha-Pisani parameter. So you see that we go below 1% in precision for the alpha-Pisani parameter. And this allows us to get a measurement of omega m that is, after all, pretty tight, considering that it is only obtained from voids. And we also play one further game. Because this methodology is fully model independent, what we wanted to do is ask ourselves, what happens if I actually include some of the knowledge that I have from simulations into my model? And so this is what we did here. We included two nuisance parameters that account for the amplitude of the monopole and of the quadrupole. And then we can get our final measurement that is even tighter, but of course at the expense of assuming something from simulations. So you can see that basically the alpha-Pisani parameter doesn't change much, but we do get an improvement with the calibrated version of our method for the growth rate of structure constraint. So before moving to another observable, this plot shows all the progress that we have done for the measurement and use of the void galaxy cross-correlation function. So 10 years ago, we had no points for this plot, and we now have constraints from redshift space distortion on the top plot and from alpha-Pisani on the bottom plot. And you can see that we have a bunch of analyses that have been done. And in particular, I would like to highlight the two ones I have mentioned today, the Gaussian streaming model, and then the multiples methodology. And what is nice here is that you see that we can look at the model-independent points, the low redshift one, high redshift, and the one in the middle. And you can see that if I look at that model-independent, it is the tightest constraint that we can have without assumptions on a cosmological model and without relying on simulation. But if we plug in some knowledge from—
Are those points correlated or uncorrelated, the model-independent ones?
So these ones are correlated. The one in the middle is the overall sample.
Okay, because they're surprisingly similar.
Yes, I agree. And but here, what happens is that if you look at the calibration version of these points, you can see that basically the error bars shrink a lot. It's not the same for alpha-Pisani analysis where the impact is lower. But in the case of the redshift space distortion constraints, if we plug in the knowledge from simulations, our error bars will shrink a lot. So we have to caution on the dependence of our results from simulation. I would really trust more the uncalibrated results, despite the fact that, well, because it has larger error bars. Okay, I have gone through the void galaxy cross-correlation function and all the constraints that we have so far by turning peculiar velocities from a source of systematic errors into a powerful source of information. I would like to spend a couple of minutes talking about the void size function, which is the next interesting step. So the void size function is basically the number of voids as a function of radius. And we can try to model the number of voids that we expect by considering that voids are inverse top hats under densities, and then we can evolve them in a framework considering the excursion set model. And so then we can predict how many voids we have in a binary redshift and for a certain size and for a given survey. Now, it turns out, and this is work that I did a while ago with some of my colleagues, again, all around the world in Paris and at Ohio University, we showed that, as one would expect, dark energy will impact a lot the void size function. And the reason for this is that the moment when dark energy becomes relevant and how strong it is, will change voids that are, after all, dark energy dominated objects. And this is what you see here. By changing the values in the dark energy equation of state for W0 and WA, that will basically control the time evolution for WA of the dark energy equation of state, the number of voids will change for voids of different sizes. This framework allows us to make a prediction on how many voids we're going to have. So the results I presented to you before are obtained with just 6,000 voids. Upcoming surveys such as Raman, Rubin, Sprex, Euclid will provide us of the order of 10 to the 5 voids. So we're going to have a huge increase in statistical power. And there is still some work to do for void abundance compared to the void size, void correlation function, because voids from theory are very different objects compared to voids in observations. And I have the privilege to work with students that have been really focusing the activity into trying to implement in the model something that allows us to merge the bridge between those two different quantities. So basically linking what we measure in simulations with what we have from theory. And this involves, well, first of all, considering tracer bias in the abundance model, but also rescaling voids to account for the fact that we have an actual underdensity that will not correspond to what we usually define as the radius of a void. And so basically rescaling the void size function to account for the central part of the underdense region. Now, this allows us to finally test whether the predictions we have are good or not. And this is what we did here. This is a simulation, a 2 gigaparsec simulation in lambda CDM. And you can see that we have the prediction from the theoretical model, this gray line here, and then the measurement from the simulation. And they match pretty well at large radii, but then we have a mismatch at low radii. And this is really not a mismatch of the model. It is due to the fact that simulations, in order to capture well the low end size of the void size function, they need to be really, really highly defined, and they need to be to reach low masses for halos. In particular, this part will be targeted by dense surveys such as PFS or the Roman Space Telescope. Now, we tested this and showed with Giovanni in particular that the theoretical model for void abundance works for very different thresholds. And this is observationally very powerful because it means that we can predict voids of different underdensities. So sometimes we do not have access to the deepest voids in a survey. So showing that we have a model that is able to predict the number of voids of different depths will be extremely useful when we apply this to data. And then we have tested the theoretical model in the framework of dark energy simulations. So we see these are the 4 simulations when we change the equation of state of dark energy, and we're still able to get quite good predictions in the void size functions. And this really brings me to the next steps that are necessary for developments of this field. The void size function is not at all at the level that we have for the void galaxy cross correlation function. There is a lot that needs to be done before we can fully apply this to data. And this involves, first of all, estimating bias, testing other cosmological models, but also being aware that there are a lot of observational effects that can play a role, the presence of mass and boundaries, but also the properties of galaxies. And I've had a student working with me and David on testing the properties of galaxies and the impact on the void size function. We also want to be aware of what are the effects on specular velocities, and this is something some work has been done with, and look at the impact of Poisson voids. So there is a lot of work that needs to be done for systematics effect, but also theoretical work that we need to put in order to improve the modeling of density profile that will really help for a better modeling of the void size function. So you can see that it is a very active field, and all this prepares the application to observations. So we have seen the void galaxy cross correlation function and the void size function. The third observable I would like to mention briefly today is the void-void autocorrelation function. With Christina Kreis, a student at Princeton, we have been looking at the impact of massive neutrinos on voids. And so we saw that changing the sum of the masses of neutrinos, the number of voids is going to change. So this is already an observable that we know is going to be sensitive to neutrino mass. But there is also another observable that I find particularly interesting because it has not been modeled theoretically yet. And this is the void-void correlation function. So basically, what is the probability that you have given a void center, another void at a certain distance from it? And you can see that if you have an average radius for your simulation or data set, this function is expected to have maximum at twice the mean void radius of your sample. And this is exactly what you see here in this plot from this paper with Christina. We see that the void-void autocorrelation function peaks at twice the mean radius. And this seems to be particularly sensitive to the mass of neutrinos. So my take-home messages today are: void analysis is really an active field of galaxy clustering. The void galaxy cross-correlation function is a robust tool that we can use for cosmology, and that already brings competitive cosmological constraints. We have a measurement of the Alka-Pasiski constraint that reaches 2% level, and this is really amazing. And we also have to be aware and pay attention about how important are model-independent techniques, because we can be pretty sensitive to the features of simulations if we rely on those for modeling. Velocities have turned from being a systematic effect into something that we can use as a powerful source of information to constrain the growth rate of structure. And we are also moving towards a full modeling of the void size function that will open the way to its application to data for upcoming surveys. I also mentioned the void-void correlation function as a new promising tool to constrain cosmology. And this will be something that we will really look onto for upcoming surveys such as PFS, DESI, Roman, Rubin, Euclid, and SPERX that will each provide of the order of 10 to the 5 voids to us from the galaxy distribution. It is important to highlight that each and every one of these data sets will be fully unique because voids have a hierarchical structure. And so we will be digging and extracting information from the cosmic web at a very different level, and therefore constrain our model and better understand dark energy and the lambda CDM cosmological model. Thank you so much.
Any questions? I'll ask online too. Go ahead.
How feasible is it to weigh the mass of
You want to turn on? I think that means the people online can hear us.
How feasible is it to weigh the mass of a void using lensing? Is the contrast just too small, or is it possible?
Sorry, can you repeat? How feasible it is to measure the mass?
Yeah, using lensing. You know, a void should cause light rays to diverge compared to the surroundings, and to tell you the total amount of all matter in the void.
Well, you can do that using lensing information, of course. And one caveat is that usually, unless you pair a survey that measures lensing with a spectroscopic survey observing the same patch of sky, you will then have voids that are defined in a photometric survey. And so it might be difficult to, on the one side, define voids, because on photometric surveys you have some error. But then to also measure the lensing mass. But this has been done from the DS collaboration, for example.
Okay, so it is actually feasible to measure the lensing
The
for
Penn
voids.
group did it.
Yeah, correct. Book J.
The Penn group did it.
Yeah, Book J. And,
So Amir has a question next week. Should
Yeah.
we go first? Amir, do you want to ask? Oh, it's a ask. Okay, I'm gonna ask for him. He was gonna ask, how empty does a void have to be called a void?
So basically, what the void finder does here is that it will perform a Voronoi tessellation of the field, and it will then start from the density local minima into basins. So we do not put thresholds on this kind of definition. Every local minima could be considered a void in this sense. What is really important here is more the contamination that we can get from Poisson fake voids, because we have mean galaxy separation. So we might want to worry more about this than the fact that we do not have very deep voids in this sense. So every local basin can be called a void or a subvoid.
So one of the test that would be nice to be able to do is to compute the same, take the same region of the sky, but two different galaxy samples, and compute the Alcott-Pachinsky map, estimate the Alcott-Pachinsky parameter, estimate of mega matter. I mean, right now, I think you've done this with the BOSS data, is that right?
Mhm.
So I guess the next, maybe DESI or PFS will have a wide enough range in galaxy properties that one can do this. I mean, this is one of my complaints about some spectroscopic surveys, like they're optimized only for doing VAO, because you can't do things like this, but I think PFS, for example, will have a wide enough range of galaxy type.
That is absolutely correct. A couple of years ago, I actually looked at the BOSS CMAS data, trying to see if, despite the sample being defined for VAO, if there were ways of splitting this, and it's not really feasible. One thing that we did do for this particular work, of course, it's on MOX, but is to check that the analysis is robust with respect to tracers that have different bias. So, of course, it would be very exciting to do something like that on a real data survey.
You've been part of the PFS studies.
Yes.
So it has the range to do that?
Yes, I think so.
Yeah, Lucia, feel free to go ahead after. I'm assuming we can hear you.
Yeah, can you hear me? Awesome. So I have two questions, but I'll start with the first one. How sensitive are the constraints from these methods based on how sophisticated or what void finding method you choose?
Okay, so I'll take the first one. Basically, I think that in particular for Alcott-Pachinsky test, it is extremely important to have a void finder that is able to capture the shape of voids, but also to have a center that is defined thanks to that shape. And the reason for this is that basically your signal does not come just from the central void, it really comes from the whole density profile. So if you just throw spheres, you're not going to have the same signal for the Alcott-Pachinsky test, in particular in redshift space distortions. For the abundance, it is a question I'm actually trying to answer. At first, I believed it would not be really important to just show spheres and try to model that as an abundance. But I think it might turn up into a difference because imagine you have, well, voids are not on a one-to-one basis spherical, of course. Imagine you have a very elongated void. If you were to find voids with a non-sophisticated local underdensity spherical void finder, it might end up splitting a long elongated void into small voids. And this will tilt your abundance because where you could have had one large void, you will have more like smaller voids. So I think it is important. There is no like right or wrong definition, but there is really a full understanding of the definition that you're using. And this will change depending on the application that you want to consider.
Any other questions? Go ahead.
So you use the void size and the void sphericity as observables among others, but your void finder algorithm also finds the shape, the full general shape. So can you use higher multiple moments or just the, beyond sphericity to
So basically what we actually do is we correlate the void center that is found by using the whole information of all the Voronoi cells that compose the void. And we stack voids. We see that so average voids in real space are very much spherical, so that we don't see a strong departure from that. And actually, even the velocities around voids are very well behaved. If you look at the results that we have before here, you can see that we expect. Whoops. There we go. The linear model will predict for velocities a flat hexadecapole, and this is really what we see. So actually we are using all the information here because the voids that we define for the void galaxy cross correlation function, we do not like impose sphericity on those in any point.
I have another question unless someone else wants to go ahead. This might be a trick question. So like people always complain about these voids or other analysis like these, partially because question is how much extra information do you have other than the galaxy sample? And if I take the view of we can weight the galaxy sample however way we want and find the correct transform field to get the maximum information, is this adding something to it?
So actually, there is a beautiful paper that has just come out from Paco here. It is using a spherical void finder, but it shows that there is additional information, which is something that I had been testing, but never published a paper on it. For example, if you use the halo mass function compared to the void size function. So there is definitely additional information that we were not looking at and refer to other variables.